Here is Professor Yasuhiro Iwamura with a talk on hotspots and melted regions observed during anomalous heat generation using nanostructured nickel composites and hydrogen.
Okay, thank you. Okay, I'll start. Thank you. Yasuhiro Iwamura. My title is Hotspot and Melted Regions Observed During Anomalous Heat Generation Using Nanostructured Nickel Composites and Hydrogen. And this is the introduction. Our experimental method. We use a nickel-based nanoscale multilayer thin film like this. This one was preloaded with hydrogen gas and heated rapidly. Absorbed hydrogen here moved toward to the vacuum surface. And at that time, we observed the enormously large heat generation, and it is not cannot be explained by any known chemical reactions. That's our experimental method. And during this process, we could not detect no gamma rays and no neutrons. And firstly, I would like to present the experimental results so far presented in this ICCF conference. Our experimental method is here. As I said, we preloaded hydrogen gas here and move by rapid heating and measure the excess heat phenomena on the surface. And this one is the example of the heat burst phenomena, heat burst triggered by input power perturbation. If we use nickel plate only, you can see the red line corresponds to the heater temperature. And the blue one and the green one correspond to the surface temperature. The surface temperature axis here, and some couple inside the ceramic heat temperature is here. And this brown line means input power. So if we decrease input power, correspondingly, TC, some couple, and the surface temperature decrease. And we regain the same value of input power. We can see some couple and the surface temperature return to the original value. It's a very natural, it's reasonable one. But if we use this kind of multilayer thin film, input power down and accordingly surface temperature down and some couple down, and return to the original value. After that, at this point, suddenly surface temperature increased up like this. It's a heat burst. And this heat transferred to the center. So some couple temperature also increase like this. Of course, during this process, we did not add any extra energy, but we got the heat, we got the energy like this. So we thought this phenomena correlated to the motion, diffusion of hydrogen in the region, in the nanolayer region, we think. And but in this data, we measure surface temperature measure only 2.5 millimeter small one. We use a 25 millimeter sample. So we just only measure around the surface, just 2.5 millimeter. So And this one is experimental results so far. This is the data after heat generation sample. Analysis data, SEM and EDX analysis data. We found that the very high oxygen concentration region after excess heat sample, like this. This black point corresponds to the oxygen. And if we look at this region, we cannot see any, not so much oxygen. But if we observed here and here, we detect a very high oxygen like this. So we call this one is regions of high oxygen concentration, RHOC. And if we analyze this sample by other method, this is the data of SEM and EDX. And if we look at this sample by TOF SIMS, time of flight SIMS, and we measure the depth profile excess heat sample, this one is correspond to the before experiment, and this one is after experiment. As you can see, we prepare nickel and copper samples. So nickel is here and copper is blue, and oxygen. Of course, the surface is oxidized by the air, but inside the sample, not so much oxygen here. And this is the bulk and the mud layer here, so we can find higher oxygen concentration here. But after experiment, we can see that oxygen is the largest in the sample by the TOF SIMS analysis. Oxygen and nickel and copper and the other impurities. So this data and this data are consistent with SEM-EDX and the TOF SIMS analysis. This is the data obtained so far. And today, I'd like to present about the surface temperature measurement. Whole surface we measure. We introduce a surface temperature distribution measurement system like this. So we have two samples, so we introduce two surface temperature distribution measurement systems like this. And this is a photograph of an experimental setup. We use this one, 25 millimeter sample and circle here. And we can measure all the surface by the introduce these devices. Okay. And this is the experimental result. Okay. This is a movie for surface temperature distribution during heat bursts, like this. At the point, and the lower temperature, 700 degrees centigrade, and higher here, we can see the heat burst phenomena like this. Okay, and this is the that's kind of a demonstration of heat burst phenomena. Okay, and next we increase the positional resolution, and this data is a measurement of surface temperature distribution, and in this case, excess heat is not so high, about the 2 watt like this. And in this case, this is a raw data for the surface measurement system. And one cell corresponds to the 17 or 18 micrometer. And this one corresponds to the measured temperature, about the 700 and to 600 or 700 like this. In this case, nearly uniform surface temperature distribution we found. But if we change the surface composition and something like that, and we got the higher excess heat case, you can see the non-uniform temperature distribution like this. Highest is 900 degrees centigrade, and lowest is 600 degrees corresponding. And you can see the red point and the blue point, the green point here. And if we look at raw data, these regions correspond to hot spot. And you can see more than 800 degrees like this. And the green region, 600 or 700 region. And the red point corresponds to the 700 degrees centigrade. So we can see that the very high temperature gradient between the very small distance like this. So heat flux from here to here is very high. So at least during this process, at least hotspot region release energy, very high energy, and this heat transfer to the lower region. Okay, and it's very difficult to estimate correctly, but one-dimensional analysis we can estimate roughly. If we use a very simple one-dimensional heat conduction from a hot spot to lower temperature region, we can see about 0.1 watt from hot region to lower region. So very large one. And the next topic is hotspot analysis. We can see we sometimes notice that there is a hotspots during excess heat experiment. And if we look at this hotspot 1, and this is the data for the hotspot. If we look at this by SEM, secondary electron microscopy, like this. And this is a combo image. It's a backscattered electron image. This corresponds to the lighter elements to nickel, more than nickel, lighter elements than nickel. And if we magnify these regions, and more magnified here, so you can see this hotspot maybe melting and recrystallization occurred at the hotspot. And if we if we magnify more, you can see that the melting region here. And nickel melting point is 1,450, very high. So we check the raw data around at hotspot 1 here. So hotspot region 900, 800, very high, and the other region 600 and 600 and 700. And this region, we have no data because our experimental system, measurement system, upper value is 1,000 degrees centigrade. So this region temperature is over the 1,000 degrees Celsius, I think. So this data consistent with the observation, this melting secondary electron microscope data. So we can see that at this point, melting occurred and recrystallization occurred. Okay, and if we look, and next one is data for EDX analysis. If we look at this melted region, we can see the very high oxygen. And the other point, not so much, a very low oxygen. So this data is correspond to the previous data, consistent with the previous data I obtained here, this one. So maybe, I don't know why oxygen, so many oxygens detected. Anyway, at the point, at excess heat or anomalous heat generation point, we detect a very large, very high level of oxygen. And recently, we look at, we analyze this oxygen region. We can see the isotope ratio is different from natural one. This data is, we have oxygen 18 by oxygen 60. Oxygen 60 is a major oxygen, and 18 is a little bit slower, a little one. And this line corresponds to the natural abundance. And region position 2, you can see large oxygen 18 by oxygen 16 here. So it is not the natural one, maybe nuclear effect, nuclear reaction, the result of a nuclear reaction. So we are now detecting or analyzing isotopic ratio about the very high oxygen region. Okay. So I'd like to conclude. The surface temperature of nickel nanocomposite sample with heat generation had an extremely high temperature gradient. This is because enormous large energy was generated in the higher temperature region and transferred to the lower temperature region. And such region of high temperature, or to put it another way, several hot spots were often observed in some cases. In some cases, hotspot temperatures exceeded 1,000 degrees centigrade, the upper limit for measurement. Furthermore, some observation of the area near the hotspot after the experiment showed that the surface had melted and recrystallized. This suggests the temperature near hotspot exceeds 1,044.55 degrees, the melting point of nickel. And a very high oxygen concentration were observed in the melted area at the hotspot. And this is consistent with previous results. And furthermore, this oxygen is not natural one. We should consider, we should analyze more and more, but oxygen 18 by oxygen 16 is larger than natural one. And this is an acknowledgement. This work is mainly supported by the TEET, Thermoelectric Energy Technology Foundation. And we'd like to acknowledge the Clean Planet and Tohoku University and Yokohama City University and Ichimura Foundation and Iwate Foundation. Thank you very much.
Thank you very much, Professor Iwamura. We have time for a few questions.
I have a question here.
Do you want to go?
I have,
Oh, Konrad?
I am very happy about your results about oxygen because it is the same we have observed as well. So oxygen definitely, in our case, we can say there is enhanced this electron screening we measured.
Yeah, yeah.
The point is, the figures you have shown us, this small hotspots at very high resolution. You see that the areas are very small. There are 14 micrometers.
Yes,
yeah?
yes, yes.
So it corresponds to energy absorption. If there's something produced in any kind of reactions, that should have absorption length of 14 or 10 micrometers, something like this. This may be an indication for that what we are looking for. So whatever you should produce, this energy absorbed in this small energy region. The first point is my point. But another point you have mentioned about this oxygen 18
Yes.
and oxygen 16.
Yes.
I think there is a very natural process because you have always a composition of both isotopes you have presented. And the effect that oxygen 18 is migrating to the surface is observed many times. You have, because the fusion is different for oxygen 18 and 16, this isotope effect. And oxygen 18 is going to the surface, oxygen 16 go down to the bulk.
So you are talking about the difference between the oxygen 18 mass difference?
Yeah, there is a large difference observed in already 90s or something like this,
And, thank you.
Yeah, something like this. So thank you very much for very exciting presentation. It is very good, very, very nice results. And I think we have now indication, small absorption lengths. We are looking for the solution of this puzzle. Thank you.
Thank you. Thank you for your comment.
Okay. I have a very technical question. After you observe a very high temperature, such area is damaged forever or again can give a chest hit?
Pardon?
When you observe some area where the temperature was over 1000, such area later is damaged or still can work?
Yes.
Damaged forever?
I did not detect in detail about that problem, that question. But because according to our experience, high spot region from the beginning, high spot region, high temperature region continue to high temperature region. But this one is a very limited case, melting point, maybe destructive. So I don't know exactly. I can't answer your questions.
Yes, may possible little?
Yeah.
No.
Please ask your second question afterwards, so we have time for the last question.
Yep. Very interesting. Do you know where the oxygen is coming from? Is that from the bulk nickel or is that transmutation reaction?
At this point, I cannot conclusive result, but I think it is a result of transmutation, maybe. But it's very difficult to explain this phenomena.
Thank you.
Okay, very quick.
Always about melting area. What about the copper?
Copper?
Yeah, what happened?
Copper. Here, you can see the copper data here. This is the original level of copper, and after experiment here, but in the nickel bulk region we have no coppers, but as you can see, we detect the copper here. So copper diffuse.
Diffuse.
And that's the
Okay, thank you.
answer.
Okay, thank you very much.
Thank you.